Okay, so we're looking this time at an airline policy. If you've ever traveled, I know no one's traveling recently, but if you've ever traveled, we know that they're very picky about their baggage constraints, right? So we're looking, and again, I want to focus on what is this main constraint we're trying to find, right? And in this case, do you see greatest volume sitting in here, right? We do want to find the dimensions, we do want to find the volume, but that greatest volume, that's the thing that we're trying to maximize. So let's write that. Maximize volume. This falls under, as far as geometry is concerned, a rectangular prism. And the volume for this in general is V is length times width times height. But you'll notice because the length and the width are actually the same, we can get away with width times height just based on the given info. So we're going to end up using V is W squared H. Okay, this is going to be our objective function. Now, we also want to figure out, well, what other constraints, what other information is given here so that we can kind of work around it, right? So this says all baggage must be box shaped, which we'll take care of with our dimensions, right? But we have a sum of length, width, and height not exceeding 64 inches, right? So again, making sure that those constraints are actual equations. So we also have the sum of the length, the width, and the height, so length plus width plus height. I'm going to call it sum for just a moment, remembering though we have this width again substituting in for the length, so the sum is W plus H, so we can say 2W plus H, right? And in fact, we can go better than that because the sum, we do have an actual value attached to it. So we can actually say 64 equal to 2W plus H. This represents a constraint. Just like last time, what we actually want to do is we want to try to find a way to connect this constraint back into this question up here. So I'll notice both of them have W's, both of them have H's. So often a question that we ask is, within this constraint, what can we solve, or what can we easily solve for? Forgive my preposition at the end, but again, and easily we're trying to think like few steps, right? We're not trying to make an overly complicated question. Well, I would point out that this H could be isolated if we just move that 2W over, right? So we could have 64 minus 2W is equal to H. And what that allows us to do is it allows us to substitute this H in to our objective function. So I've got my objective function. We've got V is W squared, and instead of H, we're going to write 64 minus 2W. Okay, so if we distribute that and we clean it up just a little bit, we get V is 64 W squared minus 2W to the third power. Okay, so just like before, now we want to find the first derivative, so dv with respect to w, and our critical numbers, right? So we need to find our derivative. So dv dw, and last time I made this note, we're going to differentiate with respect to w. So is equal to 64 times 2 is 128w minus 6w squared. And because we're finding those critical numbers, we're going to set that equal to 0. We can factor out a 2 between these two. 128 is not divisible by 3, so I can't take out a whole 6, but I can take out a 2w. This leaves us with 64 minus 3w, and they're both equal to 0, right? So according to zero product property, right, we get, we can write that 0 product property, we get 2w is equal to 0, or 64 minus 3w is equal to 0. Well, this tells us w is 0, right? And again, we run into that trouble of feasible domain, right? Not in feasible domain, right? That would mean that the base of our luggage is 0. Doesn't make any sense, right? So we actually end up just tossing this one. We'll see that happen again. We saw it on the last example, right? If we keep solving this, we get 64 is equal to 3w. And this isn't going to go in evenly, but that's okay. So we get w is 64 over 3. Okay? So this is our claim, right? We are claiming that this is going to give us the maximum volume that we can have, right? So let's test it. This is our first derivative, right? So we've got dv, dw, we've got 128 w minus 6w squared, right? So let's apply, just like we did last time, the second derivative test. Again, this is a really kind of quick test to use because you just have to take the second derivative. You could apply the first derivative as well. You'd have to use your critical number, which is this right here, right, to break up the interval and test if it's increasing or decreasing. Generally, I find that it's more work and not worth it. I usually just do the second derivative test. So if we take that second derivative, we get d squared v dw squared equal to 128 minus 12w, right? And we want to do this at w is 64 thirds, right? So d squared v dw squared, 128 minus 12 times 64 over 3. So this is going to cancel, right? This is going to be 4, and 4 times 64 is 256. So what we end up with is d squared v over dw squared is 128 minus 256. And again, I only care that this is negative, right? So according to the second derivative test, 2 dt, w equal to 64 thirds is a local maximum, right? Remember that second derivative test is kind of backwards, okay? So that means that this is in fact going to give us that maximum value we were looking for. So it did ask us for the overall dimensions, and it also asked us what is the actual volume and what are the actual dimensions, right? So we've got part of that done. Let's use this relationship here. So h is 64 minus 2w, and let me slide all the way down here. So we're going to use h is 64 minus 2w, so h is 64 minus 2 times 64 over 3, 64 minus 128 over 3, which if I just get a common denominator, we get 192 minus 128 all over 3, which gives us 64 over 3. So this is a second value. I need to add units to the very top of this one. Our units in this case are inches, so height is 64.3 inches. Width is 64.3, also inches. We'll kind of just tag that on the bottom there. And then the last thing that it wanted us to find is the volume. So volume was originally length times width times height. We adjusted to make it w squared h. So v is 64 over 3 squared times 64 over 3. So we're essentially looking at this cubed. 64 cubed is 262,144 over 27. So your volume is approximately 9,709 point, let's go to 2 decimal places. I'm going to round it. so 0.04 inches cubed. So I do realize that in the last two examples, we ended up with the same values. That's not going to happen every time. All right,